The universe just screamed, and for 1.2 milliseconds, every rule we thought governed the cosmos suddenly looked fragile. At exactly 3:47 a.m. on May 11, 2026, deep inside the Dominion Radio Astrophysical Observatory near Penticton, British Columbia, a signal slammed into Earth after traveling 3.6 billion light-years across space. It did not arrive slowly. There was no warning, no build-up, and no gradual rise in intensity. One moment, the sky was completely quiet, and the next, an explosion carrying the energy of 10,000 suns ripped through the radio spectrum. In less time than a human blink, this burst released more energy than humanity has produced since the first controlled fire on Earth. But what terrified astronomers was not just the raw power of the signal, it was the pattern hidden inside it. As the CHIME telescope captured the burst, researchers noticed something that seemed almost impossible. The frequency drifted downward in a smooth, organized sequence, sliding from high to medium and medium to low, almost like a sliding whistle echoing through space. Natural explosions simply do not behave this way. Supernovas do not sing, and black holes do not whistle. Yet here was a cosmic event unfolding with a structure, rhythm, and timing precise enough to resemble a mechanism rather than chaos. That single realization changed everything. Inside observatories around the world, data flooded through fiber optic cables at incredible speed. Scientists immediately contacted FAST, the 500-meter aperture spherical radio telescope hidden inside the mountains of Guizhou province in China. The world's largest radio dish turned toward the exact same region of sky. Teams stripped away cosmic interference, recalibrated their measurements, and asked the one question nobody could avoid. What did this signal actually look like when it left its source? The answer stunned them. Inside that single 1.2 millisecond flash were three separate subbursts packed tightly together, not random spikes and not scattered noise. Three organized blasts arrived in descending frequencies within just 50 microseconds. The signal behaved less like an explosion and more like a controlled broadcast. It sounded almost musical, as though the universe itself had briefly spoken in descending tones. That kind of modulation should not exist in violent astrophysical events. To create a frequency shift like that requires internal structure, geometry, and a system capable of altering emissions in real time while releasing unimaginable levels of energy. Whatever produced this burst was not behaving like the simple stellar catastrophes described in standard textbooks. The deeper scientists looked, the stranger the picture became. For decades, humanity believed the radio sky was mostly quiet, imagining space as a calm background hum, occasionally interrupted by distant cosmic events. But that assumption has collapsed completely. The modern universe is violently active every second of every day. Somewhere above Earth, every 10 seconds, a star tears itself apart. Magnetic fields rupture and shock waves race outward near the speed of light. Invisible blasts carrying more energy than thousands of years of solar output explode constantly throughout the cosmos. We cannot hear them with human ears, but radio telescopes can. Once scientists began listening carefully, they realized the universe was overflowing with these signals. Fast radio bursts, or FRBs, are now one of the greatest mysteries in astrophysics. To understand why these bursts matter so much, you need to understand how scientists measure them. Space may look empty, but it is filled with a thin fog of free electrons drifting between galaxies. When a fast radio burst travels through this cosmic medium, higher frequencies move slightly faster than lower ones. Over billions of light years, that tiny difference stretches the signal apart. High frequencies arrive first while lower ones lag behind. Astronomers measure that delay very carefully, calling it the dispersion measure, and from it, they can calculate exactly how much matter the signal crossed during its journey. In other words, these bursts act like cosmic sonar. Scientists are using violent explosions from distant galaxies to map the invisible structure of the universe itself. Once scientists remove the frequency smearing caused by space, the original signal can be reconstructed. When they reconstructed this latest burst, they found clear organization hidden inside the chaos. That discovery points directly toward one of the most extreme objects known to science, magnetars. When massive stars die, they collapse into neutron stars, objects so dense that a single teaspoon of their material would weigh as much as Mount Everest. A magnetar is an even more terrifying version of a neutron star. with a magnetic field so powerful it would rip apart molecular structures from thousands of kilometers away. These are among the most violent objects in existence. Sometimes the crust of a magnetar fractures under the pressure of its own magnetic field. Imagine an entire dead star cracking apart under unimaginable tension. When that happens, a shock wave erupts through the surrounding plasma at nearly the speed of light. That shock wave generates the radio burst detected billions of years later on Earth, and as the shock wave expands and cools, the frequencies naturally shift downward, which is why the signal seems to sing. But even this explanation leaves one massive mystery unsolved. Magnetar bursts detected inside our own galaxy are dramatically weaker than the bursts arriving from billions of light years away. The difference is enormous. Distant bursts can outshine entire galaxies, while nearby ones barely register by comparison. That should not happen naturally. Some scientists believe we only detect the brightest distant bursts because weaker ones fade before reaching Earth. Others think young magnetars formed in the ancient universe may have rotated far faster and carried more unstable magnetic fields than the older magnetars we observe nearby today. Then there is another theory gaining serious attention: binary neutron star collisions. Imagine two neutron stars trapped in orbit around each other for millions of years, spiraling inward slowly as gravitational waves drain their energy. In the final moments before collision, their magnetic fields collide violently, generating catastrophic electrical currents. Just before they merge into a black hole, they release one final radio scream powerful enough to cross billions of light years, and then they disappear forever. That theory explains why some bursts repeat, while others fire only once. Repeating bursts likely come from surviving magnetars, while single bursts may come from catastrophic stellar mergers. The universe is not using one mechanism, it is using many, and that realization changes how we see reality itself. These signals are not random noise anymore, they are tools. Every burst helps astronomers map invisible matter between galaxies. Every signal reveals conditions impossible to recreate on Earth, and every millisecond flash acts like a window into physics operating at energies humanity cannot produce in any laboratory. Observatories across the planet are preparing for the next stage as new radio arrays come online in Africa and Australia, while CHIME continues scanning the sky 24 hours a day and FAST remains locked onto deep space. Tens of thousands of bursts are expected to be discovered over the next few years. But here is the part that truly keeps scientists awake at night: the repeating signals, the organized cycles, and the precise timing. Some of these bursts are no longer behaving like isolated stellar accidents because they repeat with clockwork precision. When the universe starts acting like a clock, physicists begin asking a very dangerous question: what built the mechanism? For years, astronomers believed fast radio bursts were isolated cosmic accidents, violent one-time explosions caused by collapsing stars or catastrophic mergers deep in distant galaxies. That explanation made sense at first because the bursts were short, unpredictable, and impossibly powerful, appearing without warning and vanishing almost instantly. Most scientists assumed each signal represented the final moment of some dying object tearing itself apart somewhere in the darkness of space. Then the universe broke that assumption completely. In 2012, researchers studying archive data found something impossible. A source later named FRB 1102 did not disappear after its first detection. It fired again, and then dozens more times over the following years. Suddenly, the entire theory behind fast radio bursts began to collapse. If the source survived its own explosion, then whatever was generating these signals was not being destroyed in the process, meaning the mechanism could recharge. Once scientists realized repeating bursts existed, the search intensified across every major radio observatory on Earth. Telescopes scanned continuously, processing massive streams of cosmic data every second. CHIME in Canada became one of the most important instruments in the search. Unlike traditional telescopes with moving dishes, CHIME uses 4 giant half-pipe-shaped receivers fixed to the ground, relying on Earth's rotation to sweep across the sky without motors or moving parts, using pure computation power to listen to the universe around the clock. The more data poured in, the stranger the pattern became. Researchers discovered that some repeating bursts followed schedules so precise they looked almost artificial. One source in particular changed the conversation entirely. FRB 1891 fired in a rigid cycle unlike anything astronomers had ever seen before. The signal remained active for exactly 4 days, releasing bursts toward Earth with incredible consistency, and then without explanation, it went silent for 12 days. After that silence ended, the exact same 4-day activity window opened again perfectly, repeating every 1635 days with astonishing precision. That level of regularity deeply unsettled astrophysicists because random stellar violence does not behave like a clock. Supernovas do not operate on schedules, and chaotic explosions do not switch on and off with mathematical accuracy over billions of light years. Yet this signal did exactly that. Once scientists confirmed the timing was real, a new possibility emerged. What if the burst source was part of a binary system? Imagine two extreme objects locked together by gravity, where one could be a magnetar with magnetic fields so powerful they distort matter itself, while the other might be another neutron star or even a black hole. As the two objects orbit one another, their magnetic environments shift constantly. Sometimes the radio beam points toward Earth, and other times it rotates away, hidden from our view. That simple orbital motion could explain the repeating windows. For 4 days, Earth aligns with the beam and receives bursts. Then the system rotates, the signal disappears, and silence follows until the cycle repeats again. Suddenly, astronomers were no longer observing random explosions. They were mapping orbital mechanics in distant galaxies with extraordinary accuracy. Think about how incredible that really is. Humanity cannot directly photograph most of these systems because they are billions of light years away, and no optical telescope has enough resolution to see them clearly. Yet, by studying repeating radio bursts lasting milliseconds, scientists can calculate orbital periods, magnetic behavior, and stellar interactions happening across the observable universe. We are effectively listening to the heartbeat of distant stars. The source of those signals may be among the most extreme objects ever discovered. Magnetars are difficult to fully comprehend because nothing on Earth compares to them. A neutron star already represents matter compressed to absurd levels. Imagine taking a star more massive than our Sun and crushing it into a sphere only 20 kilometers wide. Gravity becomes so intense that atoms collapse, electrons merge with protons, and matter itself changes form. Now add a magnetic field trillions of times stronger than Earth's, and that is a magnetar. Its magnetic pressure is so violent it can physically deform the star's shape. The crust is an ultra-dense lattice of neutrons strained under impossible forces. When that crust fractures, the resulting energy release is catastrophic beyond imagination. Scientists call these events starquakes. A magnetar's magnetic field reconnects violently during a fracture, launching a shock wave through the surrounding plasma at nearly the speed of light. As the shock wave expands outward, the radio frequencies drift downward naturally, high frequencies collapsing first, then medium, then low. That descending whistle detected by chime is essentially the sound of a dead star releasing unimaginable energy into space. But one major mystery still refuses to disappear. Why are distant fast radio bursts so much stronger than nearby magnetar flares? In 2020, astronomers detected a magnetar burst inside our own galaxy for the first time, confirming that magnetars can indeed produce fast radio bursts, but the event was dramatically weaker than the signals arriving from billions of light years away. Some distant bursts outshine entire galaxies for brief moments, creating an enormous energy difference that nobody fully understands. One explanation is observational bias, where weak bursts from distant galaxies may simply be too faint to detect, meaning Earth only notices the brightest examples. In that scenario, the universe could be flooded with weaker radio bursts all the time, while our instruments remain effectively deaf to most of them. Another theory gaining traction suggests young magnetars formed in the early universe may have been far more violent than the older ones near Earth today. Right after a supernova, a newborn magnetar could rotate thousands of times per second while carrying wildly unstable magnetic fields, conditions that might generate bursts powerful enough to outshine entire galaxies before the star gradually settles over time. Then there is the most extreme theory of all, where some fast radio bursts may come from the final instant before two neutron stars merge into a black hole. As they spiral together, their magnetic fields grind against one another with unimaginable force, building massive electrical currents rapidly until a final burst of radio energy erupts outward across the universe just before collision. One last scream before silence forever. That theory explains why some bursts repeat while others never return. The universe may not rely on one single process to create fast radio bursts, but may instead use several completely different mechanisms at once. That complexity is exactly why scientists are so fascinated by these signals. Every burst is more than just an explosion. It is data, acting as a natural experiment operating at energies impossible to reproduce on Earth. These events allow researchers to study magnetic fields, gravity, plasma physics, and relativistic shock waves under conditions humanity could never create in a laboratory. Perhaps the most important discovery came from something hidden between the bursts themselves. When astronomers mapped thousands of these signals across space, they accidentally solved one of cosmology's oldest mysteries. For decades, astronomers faced a problem that refused to go away. According to every major model of the Big Bang, the universe should contain far more normal matter than scientists could actually see. Researchers counted everything visible, stars, galaxies, gas clouds, dust, and planets, and then compared those totals to cosmological predictions, but the numbers did not match. Nearly half of the ordinary matter in the universe appeared to be missing. This was not dark matter or exotic particles, but regular matter made from protons, neutrons, and electrons that simply was not there. This mystery haunted cosmology for years because the math behind the Big Bang is remarkably accurate. Scientists could predict how much ordinary matter should exist based on the earliest moments of the universe, yet telescopes could only account for about half of it. Somewhere between galaxies, enormous amounts of matter had vanished from observation, and incredibly, the answer came directly from fast radio bursts. At first, FRBs looked like little more than violent flashes scattered randomly across space. But as more observatories came online and detection rates increased, astronomers realized these signals could be used for something much bigger than studying neutron stars. Every burst crossing the universe carried hidden information about the space it traveled through. To understand why, imagine a beam of light moving through fog. The thicker the fog, the more the light becomes distorted and delayed. Space works similarly. The universe is not completely empty, as an enormous network of extremely thin ionized gas known as the intergalactic medium exists between galaxies. This material is spread so widely that it barely emits light and almost never blocks light strongly enough for ordinary telescopes to detect, making it practically invisible. But fast radio bursts interact with it perfectly. As an FRB races through billions of light years of space, its higher frequencies move slightly faster than its lower frequencies because of all the free electrons scattered throughout the cosmos. By the time the signal reaches Earth, the burst has stretched out, with high frequencies arriving first and lower frequencies following behind. Astronomers call this effect dispersion, and by measuring that tiny delay with incredible precision, scientists can calculate exactly how much matter the signal passed through during its journey. That changes everything. Suddenly, fast radio bursts became more than mysterious explosions. They became cosmic probes capable of mapping the invisible structure of the universe itself. Every burst acted like a flashlight shining through intergalactic fog, revealing matter hidden between galaxies. When researchers analyzed enough bursts from known distances, the missing matter finally appeared. The delays matched perfectly with predictions for the invisible cosmic web theorized decades earlier. Astronomers realized the universe's missing ordinary matter was spread throughout gigantic filaments of ionized gas connecting galaxies across unimaginable distances. The matter had never truly vanished. It was simply too diffuse and too faint to detect directly, and fast radio bursts finally solved the mystery. Think about what that means for a moment. Humanity discovered half the missing normal matter in the universe, by listening to millisecond radio screams from dead stars billions of light years away, turning cosmic violence into a scientific tool. That realization completely transformed how astrophysicists viewed FRBs. These bursts were no longer treated as isolated curiosities, becoming one of the most powerful instruments available for studying the deep structure of reality. Now, the technology detecting them is advancing faster than ever before. CHIME in Canada continuously scans the sky every day, processing enormous streams of raw cosmic data in real time, while FAST in China, the largest single-dish radio telescope on Earth, pushes sensitivity levels even further. New arrays are being constructed across Africa and Australia, creating a global network designed specifically to capture and analyze fast radio bursts with unprecedented precision. Scientists expect tens of thousands of detections within the next few years alone, and with every new signal, the picture of the universe becomes stranger. The more researchers study FRBs, the more they realize these events are deeply connected to some of the most extreme environments in existence. Magnetars, neutron star collisions, relativistic plasma jets, and gravitational interactions at energies impossible to recreate on Earth all appear tied to these signals in different ways. Each burst carries information about physics operating at the edge of what humanity understands, and in some cases, the signals themselves behave in ways that are almost unnaturally structured. That is the exact part making many scientists uneasy. Remember the downward frequency drift first detected inside the bursts? The smooth transition from high frequencies to low frequencies compressed into microseconds.